Hi, this video is about harmonics in physics. Harmonics are really interesting because they help us understand music better. It helps us understand why different instruments sound different from each other even when they're playing the same note. To help illustrate this and to understand harmonics, let's first look at a slinky. So if you take a string, or in this case a slinky, and hold it in tension, it's attached to a chair right here, and I'm holding it on this end. If I create a disturbance over here, that disturbance moves down the slinky, hits the chair, and then bounces back, as you can see. Now, if I time it right, when I send one wave down, if I also send another pulse at the same time so that I can constructively interfere with these two waves, I can create a bigger wave and a bigger wave. If I keep doing little pulses with my hand, I can create what's called a standing wave. So let me show you what that looks like here. So this is the first possible standing wave where you have just half of a wavelength here. And it's half of a wavelength because at any one time you have a peak but no, or a crest but no trough, or a trough but no crest. You don't have a complete wave. This would be half of a wavelength. Now if I took this standing wave here, and if I were to double the frequency of my hand, observe what happens to our wave pattern here. So now we have a standing wave, where we call it a standing wave because it looks like there's just a wave that's standing still. It's not moving back and forth. Instead, it's just kind of going up and down in one place. And I want you to notice right here in the middle, there's a place where the slinky really isn't moving at all. There's no displacement. And so think no displacement, think node, because that's what we call this point. So I'll do that again. So right here, there's no displacement in the slinky. So this kind of wave, this is called the second harmonic. If I kept going, if I now tripled the original frequency, notice what happens now. So we had two half wavelengths there. If I triple it, see, there's a node right here. It's harder to see because it's going pretty fast, but I had three half wavelengths, and I can keep going with this and get 4 or 5. So if I'm good, I can get like 6 or 7. But so because there is some constraining conditions there where each end has to be fixed, that means only certain possible waves can fit on this string, and I'm talking standing waves here. So the first possible wave would be just a simple crest or a trough. This wave is going up and down, so in this point I've drawn it up, but it also, fluctuates down as well. That's the dotted line here. So this wave right here is actually just half of a wave because we still need another trough to make it a full wave. So I would call this 1/2 of a wavelength here. But if we, like you saw, if you doubled the frequency, you're going to be able to actually fit more waves on there because you're shortening the wavelength of the wave as you increase the frequency. So you actually are able to fit 2 half wavelengths on here. Now I've written it like this on purpose. I know 2 halves is just one whole wavelength, but I wrote it like this because you can see a pattern start to emerge. So you keep going with this and you can get 3 half wavelengths, you can get 4 half wavelengths, you can keep on going on and on for infinity basically. And so we have a name for these different combinations that are possible here. These are called the harmonics that a wave could exist on a string. So logically, this is the first harmonic, second harmonic, third harmonic, fourth harmonic, and so on. And one other kind of term that you need to know, and I've already mentioned it a few times, is this idea of a place where there is no displacement on the standing wave. So I've labeled it here on the second harmonic. All of these locations are known as nodes. And then sometimes we call these other places right here, like this place right here, we call that an antinode because it is moving a lot at maximum amount. But a node is where there is no displacement. So if we wanted to keep on going with this up to infinity, right, how could we represent this pattern? The best way to do that would be to say, that the nth harmonic would have n over 2 wavelengths. N can just be any number that's a whole number, 1, 2, 3, and so on. So we call this the nth harmonic. And there's also one more little detail we can add here. So you can see I've labeled at the top here, this capital L represents the length from one end of the string to the other end of the string. This is how long this string is when it's fixed at both ends. And so that length is something we can often measure for like a guitar or a piano. You can measure how long the string is. So it's an important measurement in physics. And that length is related to the wavelengths that can fit on those strings, a standing wave wavelength. So we can equate these to say, okay, 1/2 of a wavelength here is equal to the full length of the string. So a way of writing that would be to say L equals n over 2 wavelengths. And so this is kind of like an equation we can use to summarize the relationship here. So let's look at another way to rewrite this equation to make it a little bit more useful for analysis and understanding what's going on with music. We also have this wave equation here, which says that the speed of a wave is equal to the frequency times the wavelength. But if we rewrite this equation to solve for wavelength, we can insert it here into our expression that we've already come up with. So instead of wavelength, we can write the speed of the wave divided by the frequency. And the only reason we're doing this is because often we want to have the frequency, because that tells us about the pitch of a note, how high or low it is. So it's an important quantity. So doing that, we put the V over F up here into our original equation. And I'm just doing a little bit of algebra to solve for F. I want to move this F out of the denominator, so I'm going to multiply by F over here. That means I'm going to multiply it by on the other side as well. So I end up with frequency times the length of the string on the left. But then I want to solve for the frequency, so I'm going to undo this multiplication of L by doing division of L here. Okay, so then I end up with this expression. I can combine this a little bit, combine these fractions. This is V over 1. So combine the denominators, combine the numerators. So the frequency of the nth harmonic is equal to n, the harmonic number that we're dealing with, times the speed that the waves move in the string, divided by 2 times the length of the string. So these are things that are easier to measure, and it has to do with frequency. And so we're going to more often use this kind of equation when we're dealing with harmonic frequencies. So going back then to our original drawing here, I want to add in some frequencies. All right, so I'm going to add in some frequencies over here. I'm just going to make up some frequencies. I'm going to say that this first one is, the first harmonic is a frequency of 50 hertz. And because it's the first harmonic, another name for the first harmonic of a standing wave is the fundamental frequency of this particular string. So the fundamental frequency is usually the frequency that we hear. It's the most intense of all the frequencies, or it's the one that we perceive to be the sound that's being emitted. And so if this is 50 hertz, then this one would be 100 hertz because it's times 2. The second harmonic is 2 times the frequency. The third harmonic is 3 times, so that would be 150 hertz. And then 200 hertz, and so on. The pattern continues again. So these are the kinds of waves that are possible on a string or a slinky, as we've seen. But something a little bit more interesting happens when it comes to musical instruments. On musical instruments, strings, I'm speaking specifically of stringed instruments for this video. Stringed instruments naturally vibrate at multiple harmonic frequencies simultaneously. So you don't have just, think like a guitar string. You pluck a guitar string, you don't have just one harmonic frequency happening. You have multiple harmonic frequencies happening all at the same time. And that produces a complex sound wave, usually one that's pleasing, that we like to hear. And this is where we start to understand a little bit more about how instruments work. each type of instrument has its own preferences for certain harmonic numbers, giving the instrument its unique sound or timbre. Timbre is also called the tone color, or just the characteristic sound that that instrument makes. So for example, these graphs are not exactly right, they're just approximate, but I have a middle C note being played by 3 different instruments. They're all playing the same exact note, but we have a piano, guitar, and xylophone. You hear 3 different instruments. And the reason for that is, even though they're all playing 256 hertz, which is middle C, they also have these other frequencies at higher levels, higher harmonic numbers, that are also being sounded and played at the same time. And so a piano might have, the strongest harmonic frequency would be number 1 and 2, but it also has a really strong 5th harmonic sound, just naturally. A guitar might have, relatively low numbers for 1, 2, and 3 harmonics, but higher levels for 4 and 5. So down here I've written the frequencies, but you know that these are just the harmonics, right? 1, 2, 3, 4, 5, 6, and it keeps going, of course. And then for a xylophone, or maybe a more bass, I know a xylophone is not a stringed instrument, but this works for other kinds of instruments as well, including wind instruments too. But for a xylophone, it's a pretty pure note, more simple sound, not as complex. And for those, it's usually the case where you hear just one particular note and maybe a little bit more of an extra frequency here, but that's about it. Usually the rest of the harmonics are not there. So the simpler the instrument, the purer the harmonics are. And you can definitely hear that with a tuning fork. So when I hit a tuning fork, you hear multiple frequencies at once. You hear a high note, but really there's also a low note being played as well. And that's really it. For a simple sound, it's probably just 2 or 3 harmonics that are being sounded together that you hear. And that's what gives it its unique sound. So each instrument is like this. Each instrument has its own unique sound because each instrument has its own unique combination of harmonics. So that's all I've got for you in this video. Remember, the opposite of love is not hate, but apathy.